This is my second time to present in this seminar series. Thank Dr. Giorgio Paulos and the committee for the second opportunity. In my first talk in October in 2020, I gave a big picture about my research map. Today, I'm going to focus a little bit on my recent researches under the topic of zero carbon electric energy. This topic has been my focus, one of my focus in the past 2 years, and as well as in the near future. Before I continue, I'd like to quickly introduce myself. My name is Qifeng Li. I'm an assistant professor with the Department of Electrical and Computer Engineering. I'm also Castor Higher faculty. I'm affiliated with the BICES cluster. I joined UCF since 2018. Before that, I was a postdoc at MIT, and I got my Ph.D. from Arizona State in 2016. You may have heard that last year, U.S. government announced a goal of reaching the net zero emission by no later than 2050. So if I ask how, probably many of you will think of the renewable energy. Yes, it's correct. Renewable energy resources is important resources for us to achieve this goal. Several years ago, people may still concerned about the cost of the renewable energy resources, but fortunately, the manufacturing costs of the wind turbine, solar panel, things like that keep dropping in the past 10 years. So now it reached to a very reasonable cost, so that we don't consider they are high cost energy resources. But even if the price is not high at this moment, but there is still quite a lot of problems to utilize such kind of so-called green or sustainable energy. I'm going to use this famous stack curve produced by the California Independent System Operator to explain a little bit what problems with those renewable energy resources. As you can see, that the back of the dot is the actual net load of California in 2012. At the time, there is very low level of renewable energy. So this curve is basically the consumption of the customers. We can see that here there is a morning peak, and people wake up and cook breakfast and then return to the office for work. And then this is afternoon very late, and then after 5 p.m. people go home and cook dinner, turn on AC, watching TV, things like that. So the whole day peak happened at around 8 p.m. to 5 p.m. So thanks to the solar generation, the net load curve start dropping during the daytime. That means there is renewable generation, the solar generation during daytime. The net load means the consumption of the customer minus the generation of the solar. So which produce the body as well as the belly of the duck. And the net load is made by the fossil fuel generators. So as you can see that if we have really high renewable generation, and after around 5 people stop working, the solar also stop working, because after sunset there is no more solar energy. So for such a case, we need to have a lot of fossil fuel generator waiting. Okay, after the sunset, we need to turn on those fossil fuel generator immediately to meet the difference after the solar energy disappear. So this is one of the problem of the renewable generation. You may think about using the energy storage. When the solar is generating, store the electricity in energy storage and then produce. Yes, that's a very good solution. But we're talking about the biggest machine in human history. we're not talking about a battery of a cell phone or of just an electric vehicle. So if we want to use the battery energy storage to deal with such a huge amount of electricity, the investment is still not acceptable. So this is what reflected by the dark curves, that the temporal mismatch of the customer consumption and renewable energy is a big barrier of the utilization of renewable. Another big challenge comes from the intermittence of the renewable. For example, for the solar, when a cloud comes by, its generation can drop from full capacity into very low level or even zero in less than a minute. So such kind of intermittence also happen to the wind power. So these are problems that preventing us to use the renewable for large scale today. So the research effort of my team is to develop technology to help the power grid increase its hosting capacity of renewable energy. My efforts can be classified into two classes. The first is the engineering solution. I could give you two examples. For example, if we have multiple small microgrids, if the renewable energy in one microgrid is bigger than its the need of its customer, so we can connect it with other microgrids to share this excessive electricity to other microgrids. So I have introduced this aspect in my talk in 2020, which I provide the link here. So if you're interested, you could go to watch that presentation. And today I'm going to focus a little bit on this engineering solution, which is the coordination between power and water systems. The second class of my research effort is to propose advanced computational or mathematical tools. Also two examples. First, the convex optimization for fast solution. The basic idea of convex relaxation or convex optimization is similar to the linearization. Okay, you have a very hard to solve nonlinear problem. You linearize it, it becomes easier to solve. But of course, the linearization is not accurate. Sometimes it is quite inaccurate. And the idea is quite similar. We approximate the nonlinear, non-convex problem or mathematical model into a convex one so that it can be easier to solve. But we believe that the convex model which is still nonlinear, which will provide better approximation than a simple linear approximation. So for more details, please go to watch this video. And today I will focus on these aspects, namely the data physical driven optimization for harnessing the uncertainty. So in terms of the energy water nexus, it is an NSF funded project. So water and power system are operate separately, but they have very strong connection. On one hand, the water system cannot operate without electricity, okay, because there are a lot of electricity treatment water facilities, and due to the population growth and the people need for higher volume of high quality waters, so the water sector have a goal to produce to improve their service to provide more high quality water. So that means they have a stronger rely on the water desalination, water purification, and even water cycling. All these activities will consume a huge amount of electricity. For such a situation, it provides an opportunity for the water facility to provide the so-called demand response service to power system. For example, during the dark valley, please try to turn on the water facility to consume the electricity, the excessive electricity that produced by the solar. But during night, when the wind is blowing, but people are sleeping, no one is using electricity, but the wind is blowing and producing. So please turn on your water facility to consume this amount of wind electricity. So this is the basic idea. But of course, to achieve such an interesting goal or beneficial goal, we need technologies. So we divide the operation of the system into different time resolutions. For example, for a very short time resolutions, when a cloud passed by, like I just mentioned, the solar generation drop, we immediately, the control technology detect the drop of electricity production from the solar, so we can immediately turn off the water facility or reduce the speed of the pump so that it consumes less electricity. So to help the balance of the electricity in pump rate. For a longer time horizon, we for example 24 hours, we check the optimal schedule of both systems every 24 hours. But there are some other challenges, like today, the water system and the power system are basically operated by different utilities. So if we are trying to optimize these two systems or coordinately control these two systems, you need to develop technology that, well, even the one part of the system are operated by different entities, they can still work. For example, the decentralized and the distributed optimization technology that we propose here. So under such a setting, the water utility will just operate the water system, while the power utility will just operate the power system. They can achieve the global optimal solution with only sharing limited information. And this is the goal of the spatial optimization. So next, it's the theoretical tool that we have developed, the data plus physical driven optimization for harnessing uncertainty. So due to the intermittency, it introduced quite a lot of uncertainty to the decision making in the ahead of real time decision making. So this optimization and uncertainty in different environment, people call it stochastic organization, robust optimization, and constraint optimization. Hopefully, these terminologies will give you will not be so unfamiliar to you. So in our research, we also consider different type of uncertainty, like the exogenous uncertainty, which means decision independent uncertainty. For example, the uncertainty of the renewable belongs to this category. And we also consider the decision dependent uncertainty, which is called endogenous uncertainty. So our contribution on the data-driven optimization in our work is based on an existing path, which use the historical measurement of the uncertain variables like the renewable generation to capture the uncertainty when we are solving optimization. And our contribution lays in the so-called strategies, scenario selection, the SCube. So in order to have an accurate approximation, basically you need a big data set to solve the optimization problem accurately. Consider the uncertainty. We developed the SCube set module and to produce a smaller data set which can represent a big data set. But the benefit is that the problem can become much easier to solve. So in the SCube module, it can be pure data-driven approach. But pure data-driven approach have issues like data quality, robustness, and some other problems. So our strategy is to combine the physical model or the physical information of the power system as well as the data approach and leverage the advance of both. So in the SCube, it has two submodules. The first submodule is the physical information submodule, and the second it's a machine learning. So it is very hard for me to give all details in a 10 minutes presentation, but I could give you a quick example. For example, we are doing the decision making for tomorrow's power, the power system operation of tomorrow. July 16th. It's a summer day, and in the morning it is sunny and with rain expected in the afternoon. So for such a day, we're not going to pick. For example, if we are given the historical data for the past 10 years, we're not going to pick the winter day or a sunny spring day or a rainy spring day. So this information is very useful for us to pick the data set that uses input to solving the optimization. Okay, this is basically my my talk. I would like to grab this opportunity to thank a lot of people, including my supervisor at UCF